Okay. Today I'm going to read a little bit out of a book called Chemistry, Getting a Big Reaction, written by Dan Green. Okay, so here's a table of contents. Introduction, basic states, nuts and bolts, organics, nasty boys, lab rats, bright sparks, earthy resources, chemicals for life, and an index and a glossary. And here you can see some little cute animations of some sort of anthropomorphic molecule. Okay, so introduction. Chemistry by Antoine Lavoisier. Welcome to the wonderful, wild, and sometimes wacky world of chemistry. Full of alchemy and mystery, it's the oldest of all the sciences. Chemistry is a study of the stuff the world is made from, the physical and chemical properties of matter, and how it behaves in chemical reactions. This is the field that has given humankind 100,000 snazzy new materials, not to mention understanding of the inner workings of life itself. Chemists may think they have all the solutions, but Antoine Laurent Lavoisier, who lived from 1743 to 1794, had more than most. He realized that air was made of several parts, and that a very important part of it was released by plants and is also combined with hydrogen to make water. He called this part oxygen. Another one of Lavoisier's findings was simple but fundamental to chemical reactions. What goes in, the reactants, always weigh the same as what comes out, the products. Sadly, he wasn't appreciated in his day and was beheaded during the French Revolution. It was his unpopular day job as a taxman that did it for this father of modern chemistry. It's so sad. This little drawing of Antoine Lavoisier with his beaker. Okay, so chapter 1, basic states. Kicking things off is straightforward. No nonsense gang who tackle the back to basics approach. Many of these guys are things that you can see, touch, feel, and hold, the physical properties of matter. You'll find these forms: solids, liquids, and gas, the so-called states of matter. Alongside these staunch characters are the more frisky melting point and boiling point, as well as the motley ways that matter combines on Earth as compounds and mixtures. Then there's the building block of matter, the element. It's the one that really matters. So here's some upcoming topics in the book. They didn't mention plasma, but solid, liquid, gas, melting point, boiling point, Brownian motion, element, compound, mixture, and of course, my favorite, the periodic table. Okay, solid, basic states. This stubborn old goat is the lowest energy state of matter. Chunky hunk whose particles have a rigid internal structure. Heating can make these particles vibrate, and if they move fast enough, melt into a liquid. Trustworthy and dependable, I don't go for anything showy or high energy. I'm built well and meant to keep my shape. With high melting points, I definitely don't want to flow. I sit motionless instead, which is handy if you want to make objects out of me, or use me to contain placeful, slippery liquids or gases or plasmas. With my atoms closely packed together, I resist squeezing and changing volume. My atoms often have a crystal structure or a regularly repeating pattern, but certain solids, such as glass or some metals, have amorphous, random internal structure. Raising my internal energy by heating me, for example, will eventually turn me into a liquid or gas. Polymers are solids with long, flexible molecules, making them plastic. If you heat them up, they can flow past each other, but if you cool it off, they get hard. Proteins are biological polymers that are also solids found in all living matter. Pure solids that form very slowly are called crystals, like a diamond. Okay, so the densest solid is osmium, which is a little over 23 times heavier than water. The lightest solid is an aerogel, which can be 530 times lighter than water. That's amazing. And the lightest metal is, of course, lithium, which is less dense than water. If it wasn't reacting with it like crazy, then it would float. And I think it does float. It doesn't react super fast at the beginning. Okay, so liquids, basic states. This fluid fellow flows through your arteries and veins. You're made out of liquid. A medium energy state of matter that can't exist in a vacuum. Okay. It's not stable in a vacuum, I guess I would say. I think it could exist for a short amount of time in a vacuum, but that's just my opinion. It would probably turn solid once the higher energy atoms left the surface of the liquid, cooling it off, and leaving behind the lower, slower energy atoms in a vacuum, turning it into a solid, and then it would just chill. Okay, and heating turns a liquid into a gas. Freezing it turns it into a solid. Nothing much bothers me, man. Like an old school beatnik, I'm easygoing and I just go with the flow. If there are obstacles in my way, I work around them, and I change my shape easily to fit into any container you choose. I'm an important fellow. Without water on this planet, for example, life would not be possible. Life actually formed almost immediately after liquid water formed on the planet. But I am fussy about whom I mix with. Sometimes I slip right into other liquids, but sometimes I flat out refuse. You can see this in the rainbow drops of oil on dirty puddles. Mutual attraction between my molecules causes surface tension, a force that makes me form drops. I resist being compressed, and I expand when heated, typically. If you heat me up or decrease the pressure around me, eventually I'll evaporate away as a gas. When I dissolve a solid, I'm called a solvent. Liquid mercury, with its high surface tension, actually feels dry. The number of liquid elements in the periodic table that are liquid at room temperature? Blammo. 2. Mercury and bromine. Lightest liquid. Man, okay. It says ether, 0.7 times water. Maybe that's room temperature or something? A gel is a solid liquid. So there's lots of different fluid properties. Liquids and gases are both fluids. But now on to gases. Okay, this highest energy state of matter has plenty to get up and go. A guy of no fixed shape or volume with energy to burn. Turns into a liquid if compressed or if the temperature is decreased enough. I fizzle, crack, and pop. I literally hum with energy. Freed from the tiresome bonds that bind solid and liquid, my particles dart around like hyperactive bees, except much, much smaller. I'm mischievous and I can disappear right in front of your eyes, dispersing into thin air. Although I can be colored like green chlorine gas, usually I'm invisible, like the air all around you. My unconfined nature means that I have no choice but to fill any container that I'm put into. Squeeze me into a can and my particles bash against the sides, exerting a force that is felt as a pressure. Heating me up makes my particles move around faster and also has the effect of increasing the pressure. But squeeze me hard enough and you can calm me down with my exuberance enough and turn me back into a liquid. I can take the pressure. Can you? So mustard gas is a very poisonous gas and was first used as a weapon in World War I. The heaviest gas is fluorine. It's 14 times the density of air. It's interesting. What about chlorine? Or xenon? Xenon. Lightest gas is hydrogen gas. And volatile, it means that molecules form gases easily. So here is a little picture of the gas escaping from the container. It does not have a fixed size or shape or volume. Okay, melting point. Sticky fellow who is there when solid turns into a goo. Measure how easily the forces inside of the solids are broken, and it's measured in degrees Celsius or Fahrenheit, and it's not very strongly affected by pressure, but some phase diagrams will have this little tilt in the pressure part of the curve. Okay, I'm soft and schmaltzy, and my crooning will melt a solid's heart. The forces between atoms and molecules in solids are strong and stable, and so it takes energy to break them. When you heat up a solid, its particles vibrate more and more until finally they have enough internal energy to break apart. Measure the temperature as solids turn to mush, and you have found me, the melting point. So there you go. Neat little old melting point there, isn't he cute? Okay, the melting point of water at sea level is 0 degrees Celsius. The highest melting point element is tungsten, and the lowest melting point element is helium. And it's the temperature that liquid turns into a solid is the freezing point or the melting point. Okay. Boiling point, the point at which a liquid boils and turns into a gas. It's a measure of how easily the forces inside liquids are overcome to become a gas, and it's measured in degrees Celsius or Fahrenheit. And very obviously affected by pressure, because you press down on it, it keeps all those atoms in the liquid. I'm a fiery cauldron, fizzing with rage, boiling and bubbling. I vent my fury on liquid. The molecules that make up liquid are much less tightly bound to each other than solids molecules are, but they still have a definite tendency to bunch together. I teach them to stand on their own 2 feet and busting apart and breaking through the surface energy, the surface tension of the intermolecular forces at the surface of the liquid and turning them into a gas. Okay, it's a gas. Here we go. There is the little old boiling point. Anthropomorphic as can be. He looks hot. Okay, boiling point of water, 100 Celsius or 212 Fahrenheit. The highest boiling point element is tungsten again, and the lowest is helium. It's the same too. It's interesting. Probably a coincidence, right? Just kidding. Okay, condensation, when a gas turns back into a liquid. So they don't mention subliming here at this point, where I might. And they also don't mention plasma, which has, when you rip an atom apart and you take the charge of the electron away from the charge of the atom, then you end up with 2 ions. You have this negatively charged electron or negatively ionized atom and a positively charged nucleus or positively charged ion or molecule. Okay. Anyways, charge, which should be introduced right here, the model of the atom. But that's okay. Next, we're going to go to Brownian motion. And this is, of course, important. So, Stinky Brown Pants, who shows tiny particles how to move around. That's kind of funny. It makes molecules bash blindly all over the place, and the thermal energy of heat is the mixer of all the molecules in the liquid. For a chemistry thingamabob with such a sensible name, I'm a very silly character. I say things like, nip, skeep, wibble, wibble, because everything about me is random. You might not be able to tell what I'm going to do next, but you can easily predict my overall random behavior. I describe the way particles move around in a liquid and a gas. If you looked under a microscope, a tiny pollen grain would jitter around in the water as if it's alive. Well, that is what Mr. Brown first thought. Mr. Einstein figured it out, that the random walk happens because of the particles being batted around by the invisible motion of particles of the molecules in the liquid. This explains how smells spread as well in the air, a process known as diffusion, when tiny molecules bounce around and are jostled through space. Stinky molecules are jostled and dispersed until, ew, who let one go? Okay. Brownian motion is named after Robert Brown in 1827, and it was first noticed and recorded by Jan Eggenshaus in 1785, and first explained by Einstein in his Annals Mirabilis, 1905. So there you go. There's the factoids. There's Mr. Brown. Mr. Brownian motion. He's jumping around. See, this is supposed to represent an atomic path, some random walk that the atoms inside the liquid took during their course through the material. Okay. Element. This one's elemental, folks. A kind of goody two-shoes that makes up every substance. Elementary character made of made of atoms of all the same type, one of the building blocks of matter listed in the periodic table. So, pure and simple, I am the basic stuff of everything that you see in the universe. With my 118 unique versions and almost no limit to the possible combinations, there's already a mind-bogglingly number of compounds in existence. Chemists continue to make new ones by combining me in different proportions and in new ways. Each of my varieties keeps itself. Every single one of them is made up of only one type of atom. My lightest variety is hydrogen, with a single proton in a nucleus. Next up is helium, with 2 protons and 2 neutrons typically. This pattern continues all the way to the strange, unstable, and very short-lived elements with hundreds or more protons and the attendant cargo of neutrons in their central nuclei. So, the most reactive element is maybe francium. The most reactive nonmetal is fluorine. Super electronegative. It's like, give me those electrons. I need it. I need just one more. Then I'll be complete. Okay, and the number of naturally occurring elements is 92. So there was a quip about, the nucleus gives an atom its identity, but the electrons, they give it personality. So the heaviest element is so far discovered is 118, which has a virtually unpronounceable name. Unoctium. Okay. Compound. This chemical master chef combines elements into new substances. It's produced and broken apart by chemical reactions, and most substances on Earth exist in the form of compounds. Almost always atoms get together and react and chill together. My creations are the perfect pudding, the right combination of all the right elements in just the right proportions. Chemicals like to cozy up with each other, and with the help of ionic and covalent bonding, I allow them to do this in a way that benefits both elements. But once my ingredients have been fused together, it's difficult to get them separated. That's right. That's a good illusion to entropy. Okay, oxygen is a compound of 2 oxygen atoms. Total number of compounds, 61 million. It's an interesting claim. Ionic compound example is salt. That's when you have 2 atoms, one of which completely takes away the electron from the other atom, and they are happy like that. Like, sodium, who has 1 to give away and is happy, and chlorine, who has 1 to grab. And once they do that, they exchange that electron. Those 2 atoms can just hang out next to each other in a crystal, and they're perfectly stable. They just chill, like a little grain of salt on a table. Okay, a covalent bond is when the 2 atoms share the electrons, and the electrons going around, kind of buzzing around in its quantum mechanical way between the 2 atoms, and you're never quite sure where it is, but it's kind of somewhere nearby, with its charge holding those 2 atoms into a stable position, like a water molecule. It's a fixed angle that can vary a little bit with energy and bend, and as those atoms get hotter and hotter, eventually rip apart into a plasma or a gas. First, obviously. Okay, compound. How about mixture? This mixed up puppy is one smooth blender. His recipe can be separated by physical means. Chemical reactions take no part in this kind of combination. So if you mix salt and pepper with each other, they don't react or form anything new right away. Right, maybe at the small scale a little bit, but probably not much. So a mixture is a real smoothie. I blend substances together, and there's no sweat. None of compounds' heated reactions, just a relaxed merging of one substance with another. Like a snack of Halloween candy, I'm all mixed up. But each part can still be separated by physical means, such as with your sticky fingers. Liquid mixtures need to be separated using special techniques, like distillation. Solid mixtures examples are concrete or soil. Liquid mixture solution is like salt water. And a solid liquid mixture examples could be like, I might say wet concrete, or they say milk here. It's interesting. Tap water is a mixture. Distilled water is pretty much a pure molecule. So there you go. There's compound and mixture. Yeah, are they integral at the atomic level or not? Okay, so last page for tonight, I think. Oh, maybe. I'll just finish this section. Okay, the periodic table. So there it is. An elegant way of arranging and organizing all the known elements into a table. The groups run vertically and the periods run horizontally. This was invented by the Siberian super-chemist Dmitry Mendeleev in 1869. Up to, I'm a Paragrade ground serpent major, and it's my job to get the elements in order. I whip these chemicals into shape. Yes, sirree. A stickler for organization. I get all 118 elements to line up in groups, rows, and blocks. The groups, the vertical columns of elements, share similar properties, and they share similar number of electrons in that outermost shell. That's what gives them that similar properties, their electronic structure. And the periods, the horizontal structures, or the rows, represent larger and larger atoms and more protons in the nucleus of the atom, and new energy levels available to electrons around the atoms. The type of substance and its chemistry and its reactivity changes as you move up and down the groups or move along a period, depending on what the element is and what's adjacent to it and how it changes its energy state or how happy it is to lose or gain electrons from its outer shell. In fact, you can tell an element's personality based on where it is in the table. Metals cluster on the center and left-hand side, and nonmetals in the right and in the upper right part of this table especially. Okay, element number 101, Mendelevium, was named after Mendeleev, of course. And group 1 are the reactive metals. The elements in the center are called the transition metals. Those are all those guys right there. And group 18 is the inert noble gases over there, like helium, neon, argon, krypton, xenon, and radon. Right. So say the elements real fast. It's a good idea. Hydrogen, helium, lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon. All right. Okay, let's see. Chapter 2. Okay, I will end it there for tonight. Talk to y'all soon on Flipping the Classroom, Chemistry, Getting a Big Reaction. Don't forget to like and subscribe.